Hello, everyone. Welcome to this inaugural session of this Virtual Science Forum. So before we start, I'm going to just go over again how this thing will work today. I'll be the moderator of this talk, and the idea is that if you have any question, you can go to the bottom of your screen. There will be a list of participants, view participants. And at the bottom of this list of names, you'll have some symbols. And the most important one will be the one of raise your hand. And when you do that, I'll be monitoring the chat. And when I think, or when I believe it's a good time for me to stop the speaker and to mention that there's a question, then I'll introduce the participant that has the question, and there will be time for discussion. On the same time, I'll unmute you, and you'll have the discussion time. And when it's finished, I'll mute it again, and the talk will continue. That is that on this side. In the event that your microphone doesn't work, you can also ask questions via the chat, and we'll be also monitoring that. Without any further ado, I'd like to introduce our first speaker. We are very, very thrilled to have him today. Thank you for agreeing to join us in this first inaugural event. And the speaker will be Florian Marquardt from Max-Planck Institute for the Science of Light and the Friedrich-Alexander University in Germany. And his talk is going to be about deep learning for rapid exploration of topological band structures. Please, Florian, the room is yours.
Okay. Hello, everyone. Hello, everyone. Make yourself comfortable wherever you are. It's a great pleasure, and I want to thank the organizers of this spontaneously put together meeting. I think it's a very good idea. So I've been discussing with colleagues over the last year, even before this virus thing, how could we improve scientific workshops and conferences, because I'm frankly traveling a little bit too much. And so this idea of online meetups, online workshops, I find really great. And I really can anticipate that in the future, we will have more and more of these for the, so to speak, standard conventional talks. And then probably we still want to meet in person sometimes, right? To somehow explore new ideas and get to know each other, which is a little bit more difficult in such an online setting. But we could then come back to the, say, workshop format as such, the kind of thing that people organize, for example, in Benasque, where you just go for 2 weeks and meet interesting people and work together with them, and maybe there's only one talk per day. So I can really imagine that we have this hybrid system coming up in the future, and I find it really great what you are organizing today. So my talk will be about deep learning for rapid exploration of topological band structures. But before I get started, here's a picture of us at the APS March meeting near the registration desk when we were there last Sunday. I'm still currently in Denver. I'm currently in the hotel room. I have to apologize that I will not be able to be there for the full entire session. So I have to leave in 2 hours from now just to catch the plane out of Denver. But here you see us. We are not happy that the March meeting was canceled, but I guess we were happy to have a photo opportunity as proof that we were indeed there. Okay. So let me start by some introductory slides. Now, I don't really know the composition of the audience. Maybe all of you know neural networks and machine learning, then I apologize a little bit, but anyway, here goes. So if you think of your brain, you can think of your brain in many different ways, but in a very simplistic way, you can also think of it as an information processing device. So there's an input and there's an output. The input might be what you see or what you hear, and the output is then what you do in response to it. For example, you say something. Now, as an example, if you spot an arbitrary picture of a light bulb, within a fraction of a second, you immediately know this is a light bulb. And the amazing part about this is you can do this even for a picture of a light bulb that you've never, ever seen before. You've never seen this particular shape or this particular perspective or this particular lighting before. So your brain is really, really flexible. And that's amazing from the point of view of a computer scientist, because if you were to try to hard code such an algorithm that would be able to recognize all these different pictures as light bulbs and other pictures as dogs and cats, that is practically impossible to do. So even more than half a century ago, people asked themselves the question, can we implement something like a meta algorithm that would be able to be as flexible as your brain is, for example, in image recognition? And so the idea they came up with even half a century ago is an artificial neural network. So it's inspired by the real neural network in your brain. It consists of neurons denoted by these circles. They are connected. And the basic idea is that instead of hard coding the feature recognition that you would need to label correctly such an image, you will rather present such an artificial neural network with tens of thousands of training examples, each labeled correctly. And with time and with the right training algorithm, it will learn to properly label these pictures and then even extend a little bit into domains to recognize pictures that it has never seen before. So I will give a brief recap a little bit later in this talk, but that's the basic idea of an artificial neural network. It had taken really half a century, and there were ups and downs in this field of machine learning, especially machine learning using neural networks. But one of the big breakthroughs that really caught everyone's attention came in 2012. So you have to understand that computer scientists like to put up public challenges where everyone can enter this challenge with their own algorithm and try to perform in the best possible way. And a particularly famous challenge is the so-called Imagenet competition. So in Imagenet, you're given 1 million training pictures. You can do with those whatever you want to build your algorithm. And then in the end, you will be tested on pictures that you have never seen before. And the idea is the algorithm that will label most of them correctly wins. And in 2012, it was for the first time that a deep neural network was able to beat all the competition clearly. And since then, it was always neural networks that have beaten the competition. And by now, they are really better than humans in labeling these pictures. So since then, there has been a rapid proliferation of real-world applications of neural networks in many, many different areas, for example, self-driving cars or translation, speech recognition, you name it. And not surprisingly, also in physics, there has been a boom in applications of neural networks. One has to say at this point that physicists have always been interested in neural networks because of, for example, their connection to statistical physics. And there's famous examples like Hopfield's analysis back at the beginning of the 80s, connecting neural networks to spin systems. But the actual application on a large scale to many, many different challenges in physics that really took off only in the last few years. And here's one example which is particularly easy to understand. So I showed you image labeling as the prototypical application of neural networks, and therefore you are looking around in physics for cases where images play an important role. And one case is shown here. If you look at the magnetization pattern of some magnetic substance, so yellow maybe spin up and blue maybe spin down, then depending on the temperature, of course, you can be in different phases, like paramagnetic phase where the spins are completely random, or the ferromagnetic phase where they're almost all aligned. And it's no wonder that you can train a neural network to recognize these different phases. It's more interesting that you can do so in a smart way where you only train on the low and very high temperature regimes, and then still the neural network can help you to figure out where exactly is the phase transition temperature. By now, of course, people are applying this to much more complicated settings where the hope eventually is that we can also really discover phases that we haven't seen before. Here's another little example from our group from the past few years. So the concept I talked about so far is supervised learning. You can also, and supervised learning means you have all these training examples where you know the question, which is the image, for example, and you know the correct answer, which would be the label. So you know question-answer pairs. But in some other cases, you want to figure out something new on your own. You want to figure out a good strategy, for example, a good strategy to control a robot, or a good strategy to do quantum error correction. And in that case, you don't even know the answer. You cannot do supervised learning, but the alternative is so-called reinforcement learning, where you reinforce the good actions. And in this work, which I direct you to, we applied this, especially deep reinforcement learning, that is with neural networks, to quantum error correction. Okay. So now let's take a short break. And for the 10% out there that have not yet learned their neural networks, here's a very brief recap. So a neural network, as I said, consists of a set of neurons, here represented by these circles. At any given time, any neuron just holds a single number. So it's much, much more simple than a biological neural network, of course. At any given time, it holds a single number. And these neurons are arranged in layers, as you can see here, starting from an input layer, where you would feed in the representation of, for example, an image that you want to recognize. So you convert it into numbers, and you feed those into the values of the neurons in the input layer. And then there's a sequence of hidden layers, and then finally an output layer. And so there's information processing going on sequentially, going from the input layer through the hidden layers to the output layer, finally giving you the answer, for example, the label for an image. And so what goes on inside each of these computational steps? Well, here's a brief recap for that. Imagine that we want to calculate the value of a neuron in a higher layer from the values of neurons in the next lower layer. So what we would do is really two steps. The first step is we take these neuron values in the lower layers. We weight them to build a linear superposition. And then we get something that is conventionally called Z. So we have a linear superposition of the neuron values. But if that were everything, if all that a neural network would do is taking linear superpositions, that is applying linear operations from layer to layer, that would be far too simple, because then the mapping from the input to the output eventually is also a linear operation, and surely linear operations are not enough to represent arbitrarily complex functions. And so what is crucial is that in each of these computation steps, there's also a nonlinear function applied to the output of this linear superposition step. And this nonlinear function can really be very simple. It does not need to change. It does not need to be adapted to the particular problem. One possible function that people like to use is such a smoothen step function that is similar to what happens in your brain when only when the inputs to one particular neuron are large enough in their sum, then you will have the neuron firing. So that's a particular choice, but it's not the only choice. And so with this combination of linear superpositions and nonlinear activation functions, actually neural networks, and this can be mathematically proven, can represent arbitrarily complex functions if you are only able to choose these weights. And this is what happens during training. So during training, the weights are adapted in such a way that the mismatch between the output of the neural network and the desired true output becomes small, averaged over all training samples. So that was a quick recap of neural networks. It's only a 30-minute talk. So if you're really interested in learning this and you haven't yet learned it, I advertise here a little bit my website, machinelearningforphysicists.org. So that collects videos of a 12 lectures series about machine learning. Okay. So with that being said, when you first enter the field, you get very enthusiastic because apparently neural networks can do everything, especially if you look around for all these great examples. So there's a word of caution here. So machine learning is not a magic bullet. And there are multiple reasons for this. One is that training a neural network is a highly nonlinear and stochastic process. It's not well understood theoretically at all, although people, of course, are working on this because it's very important now. You could end up with different neural networks, even though you show them the same training data, but they started off with slightly different random initial conditions, or you presented the training data in slightly different random order. these networks could have different performance. They could have the same performance, but still internally be very different. So it's a highly nonlinear process. Also, the results do depend on the quantity and quality of training data. So that means if you say, I have 20 experimental examples and please train a neural network, that will not work. And then also, even if the neural network performs very well, that's not a substitute for basic understanding. So the neural network is a little bit opaque. It's like a black box. Interpretation requires care. And people are, of course, developing methods to interpret neural networks better, but it's not so easy. That being said, they can be useful and there's much to explore, so let's use them. Okay, so now I really want to go to the essential part of the talk, and that's telling you about our ideas for how to use these neural networks, these deep neural networks with many layers, how to use them to explore band structures. And so what do I mean by that? What do I mean? What you're looking at here is a silicon chip. The light gray is silicon, the dark gray are just holes that have been cut with lithography into the silicon. And so what this represents here in this example is both a phononic crystal and a photonic crystal. So it has both a band structure for sound waves and for electromagnetic waves. Here's another example which is even more complicated. So that's again a phononic crystal, but it has been specially designed. So these are still unpublished results. So here we tried to use something like a genetic algorithm to optimize the shape that you see in order to get a band structure that has topological properties. So these are the kinds of things that you can explore when you have the full power of nanofabrication techniques that allow you to implement almost arbitrary shapes. And so more broadly speaking, that would be the field of engineered materials. Yeah? So where you really have huge freedom in the design, even more freedom than the chemist has in putting together real materials. And so if you have all this freedom, what you want to do is you want to explore the full infinite dimensional design space. And if you can explore that infinite dimensional design space, you also want to optimize. You want to optimize some properties of these engineered materials. And one of the things you might be looking for these days, especially, is peculiar aspects of wave transport. So whether you look at sound waves or electromagnetic waves, in certain cases, they can have topological properties. And so the task of searching through the large space of possible materials to find those that are topologically interesting, that has been labeled by some recently topological quantum chemistry. And so the point of my talk will be to say that we can use deep neural networks to go in all of these directions for engineered materials, to explore and optimize them and even look into their topological properties. Okay. So now, what could be the challenge that you set yourself? Well, one of the simplest things is you have some periodic structure. So it has a unit cell that has a certain geometry, like the geometries that I just showed you in these real world pictures. And you want to know what's the band structure, yeah? Because maybe you want to engineer a particularly large band gap, or you want to have Dirac cones at certain spots, these kinds of things. And so the idea is that an expert maybe could look at this geometry and look at certain features and understand, for example, that there should be a large band gap between the third and the fourth band, or should understand that for certain reasons there should be these Dirac cones. So there is some qualitative understanding that an expert would have. And the question, the obvious question now, the way I set up this talk is, can we do this using a neural network? And so at this point, I should emphasize, of course, people have been asking this question before. And so what exists, what is the status quo in the literature, is really that people parameterize the geometry in terms of a few parameters. So for example, you have holes with a certain radius at a certain position, and then you can try to compute the band structure using some finite element simulations, and then let a neural network learn the mapping between these few geometry parameters and the band gap or the full bands, or maybe even topological invariance. So people have been doing this for some years. What we want to do is here really go to arbitrary geometries, because otherwise you're a little bit restricted. If you only have certain geometry parameters at your disposal, maybe later you get another idea for another design concept, and you would have to do these finite element simulations again. But really it would be much better if your neural network is able to look at arbitrary geometries. And so I want to make a small reference to what happens in computer science with neural networks. So mapping a geometry to a band structure, you could really see as analogous to something that's called image-to-image mapping. So what does that mean? So here on the upper left, you see a kind of black and white drawing or picture of the actually the Capitol in Denver. And you can train a neural network such that it is able to turn these black and white images into colored images. And the way it can do this is because it has seen so many examples of black and white images and the corresponding true color images, that eventually it starts to understand, for example, that probably what you're seeing here to the left of these stairs is grass, and grass is green. Yeah? So this is image-to-image mapping. And in a sense, putting in the geometry and extracting from that the band structure is also a sort of image-to-image mapping if you view the band structure, that is the energy as a function of momentum, as yet another image. Okay, so that, that will work. Actually, this is how we started. Conceptually, it's not very difficult. In computer science, it's being done routinely. But we're not really satisfied with this. And so there are many challenges that I will now try to make you understand. So the first challenge is, as I emphasized before, the interpretation of such a deep neural network is really rather opaque. It's not at all obvious what goes on inside. So that's a challenge. Here's another challenge that sounds a bit more technical, but if you go and calculate the band structure, starting, for example, from finite element simulations, feeding in the geometry, then really the time you need to calculate the band structure scales with the k-space resolution. So for each point in k-space at which you want to evaluate the set of bands, that is the set of energies or frequencies, you need another calculation. And so why is that a problem? Well, that's a problem because on the one hand, you don't want to spend so much time on these calculations, so you would want to go to lower resolution. On the other hand, maybe later you want a high resolution in k-space. Why would you want that? Well, for example, interesting features like these Dirac cones, they do need a high resolution. And an additional problem is that it's really hard to reliably produce, especially these high resolution features. For example, if you do something a little bit wrong, if your neural network gets things a little bit wrong, it might easily end up gapping out the Dirac cones. I see a green line on my screen. Was that me? Okay. So going further, you can try to exploit symmetries, because you know, if you are into the design of interesting topological band structures, very often that's based on producing a nice symmetric structure. So in addition to having the periodic translation symmetry, of course, you also have some, for example, rotation symmetry, 60-degree rotation symmetry. And in some sense, if you train a neural network without any extra information, that's a little bit superfluous. So it does not per se at first exploit these symmetries. So the symmetries don't really help. Eventually, of course, it will learn all the features of the band structure that result from the symmetries because it sees so many examples, but it's not completely efficient. And then you don't only want to exploit symmetries, you also want to predict symmetries. So what do I mean by that? So you have in such a symmetric crystal lattice, you're looking at the Bloch waves, and at least at the high symmetry points in K space, for example, at momentum equals 0 at the gamma point, you can classify the Bloch waves by their symmetries under the original group. Okay, so these are challenges, and the question is, how do we solve them? And so again, input should be geometry. The output we are interested in is still the band structure. But what we will do is we put one step in between. So our neural network will not directly map the geometry to the band structure, but rather it will be trained to map the geometry to some tight binding model. Namely, which tight binding model? Well, the tight binding model that upon diagonalization would give you the band structure that you also find alternatively from your microscopic brute force finite element simulation. So that's the idea, mapping geometries to the parameters of a tight binding model. And so the parameters would be just the hopping amplitudes and the on-site energies of a tight binding model. And that's a much more compact description. So here these pictures represent the different orbitals that you could have on the different sides of the tight binding lattice. And if you take into account the symmetry, then these hopping amplitudes are not completely arbitrary, but they are constrained in a certain way. So there are fewer of those tight binding hopping amplitudes. And so these are the few parameters that the neural network should spit out when I present to it an arbitrary geometry. And so in computer science, this is labeled known operator learning. So what does that mean? You know, after you've got the parameters of the tight binding model, in order to go to the band structure, you still need a final step, which is to diagonalize the tight binding model. Of course, that's much easier than the original extraction of the band structure, because such a tight binding model only has a small number of orbitals, so the matrices that you have to diagonalize are small. And the really important point here is that this operation, this extra operation, the diagonalization, is differentiable. Yeah, so I can figure out how the energies of the band structure change in response to the parameters of the tight binding model. I can take the gradient through the diagonalization operation. And that's super important because all this neural network training really works by postulating some cost function, which may simply be the difference between the true answer and the neural network answer. And in order to do gradient descent on such a cost function, you really rely on everything being differentiable. And so if you introduce such a known operator like the diagonalization, it has to be differentiable. So that's the idea here. And of course, the tight binding model accounts for the symmetries. It automatically enforces features like the Dirac cones that follow from the symmetries and so on. So it is much more efficient to do it this way. Okay. So that's the setup. Any questions at this point? So just interrupt me, but otherwise I will go on. So now you want to generate training samples. How do we do this? Well, we decided to just adopt random Gaussian fields. So you take basically Fourier transforms with coefficients that are Gaussian random variables. And then we wanted to model a situation like you would have in a photonic crystal or a phononic crystal, where basically you have two materials, maybe glass and air. So we turn this into a stepwise potential, and then you get these figures that I'm showing to the left. And then you want to...
Sorry, there is one question.
Yes, okay. Wait, I have to... Okay.
No, I'll do it myself.
Okay.
Go ahead, Anton.
Yeah, sorry, I just wanted to understand a bit more the process of deriving the band structure from, or learning the band structure from the microscopic model. So the goal here is to have a high precision of the prediction and the tight binding model is a useful intermediate representation. Is that the right way to understand the point, the procedure?
Yes, in a sense. So there are many goals, of course, not only high precision, but also eventually that we can predict the properties of the Bloch waves as well, and so on. So there are all these reasons why we want to go to a tight binding model. But one of them is that it's really efficient, because if I get the right tight binding model coefficients to match the first few bands, then I can do so possibly even by having trained only on a few K points. But eventually I can use the predictions of the tight binding model even to scan with very high resolution the full Brion zone, because it's somehow all encoded in the tight binding model coefficients. So it's really much more efficient than having the neural network try to reproduce all the really sharp features, for example, around a Dirac cone on its own. Because the tight binding coefficients can be really smooth and it still can give you these Dirac cones.
Yeah, I see.
Okay.
Thanks.
Okay, good. So here's training sample generation. Then how do we get the band structures? Well, that depends on what exactly is the situation you want to model. Here we used a Schrödinger equation. That would be, for example, photonic crystal waveguides and paraxial approximation, but you can replace it by any kind of, say, COMSOL finite element simulation. And so here's the results, the first results. You check how big is the deviation. So after training on 50,000 examples, deviation between neural network and the exact solution is 2% on unseen test examples. And it's really 1,000 times faster than the microscopic calculation. So that's good. But that's only the beginning. So here's just to illustrate these things. What I'm plotting here as a color code is in the Brion zone, the band gaps, for example, between the second and the first band, or third and the second band, and so on. And I'm plotting both the neural network prediction and the Schrödinger equation prediction, and they basically lie on top of each other. It looks a little bit more simple than it actually is, so we had to work hard to get it to this point, but it works. Okay, now we can not only exploit symmetries, I explained this, but we can also predict symmetries. So what we do is really, when we calculate the band structure, also at some high symmetry points in the Brion zone, like gamma, K, and M, and so on, we extract the symmetries of the Bloch waves. For example, we say at the gamma point, this is an S wave or P wave. And we feed this extra information into the tight binding model. The tight binding model anyway tries to represent, is represented in terms of such orbitals, for example, S, P, D, and F. And at these high symmetry points, we can then put constraints on what should be the predictions. Okay, so here's a few examples: geometries, bands, the corresponding symmetries, and then the accuracy which we can reach. So what you see here is in percentage for the different bands, first band, second band, third band, and so on, how often, for example, you get the symmetry at the gamma point or at the K point correct. So that's encouraging, because these are all in the very high 90% range. And so what can you do with this? I think I have to speed up a little bit. One of the things that people look into when talking about topological features of band structures is that you can design band inversions. So for example, you can change the geometry parameters in your unit cell so that, for example, a P and the D band cross, and exactly where they cross in real space, you expect an edge channel, in this case, a helical edge channel. And so what you can do now is, if you have an idea of how this might work, you put in your arbitrary geometry, you change the parameters, and your neural network immediately, very quickly gives you the corresponding band structure. And then you could use this to optimize, but I will come back to optimization later. So here's another thing that another big point that I want to make. So when people talk about topological properties and of waves in periodic media, most of the discussion in the past decade or so had centered on looking into reciprocal space. So looking into the features of the Bloch waves, looking into those. Only rather recently it was realized that you can also go to real space, namely by constructing the localized Wannier orbitals from the Bloch waves and looking at their properties. And even from those, you can extract then interesting topological properties. And so just to make this really clear, you can take not only a single band, but a set of connected bands. You can then construct Wannier orbitals. There's a certain ambiguity in how to do this, but you can construct what is called maximally localized Wannier orbitals. And then you can ask yourself, how do they look like? And in the simplest case, the Wannier orbital may just say sit in the center of the real space unit cell, be of S type, so have the full symmetry of the underlying point group, and that's fine. But there are other cases where these maximally localized Wannier orbitals, where there are several copies, so to speak, that sit, for example, at the corners of the unit cell and which turn into each other by applying the point group symmetry operation. And so there's a whole zoo of such possibilities, but it's finite in number and you can enumerate them. These are called elementary band representations. And so there's a whole theory out there to deal with those. And so the beauty now of the neural network is that very easily from being able to predict the symmetries of the Bloch waves, you can extract these elementary band representations and you can do statistics. You can go through tens of thousands of sample geometries that have been randomly chosen according to some distribution that you decide on. And you can figure out what are their elementary band representations. First, you figure out what are the connected bands and then what's the elementary band representations. And so one of the interesting features here is that, and this is also a rather recent development, people have realized that not always can you deform smoothly back to the atomic limit. And when this fails and then there is no elementary band representation, then this is called a fragile topological band. And so here we then find for this particular distribution a certain percentage of these fragile topological bands. Here's another thing you can do. So look at the, try to interpret the neural network results. And the problem with this is always that the neural network activations or even the output of a neural network, these are high dimensional quantities. So how can you even plot them? And so computer scientists have invented methods like so-called TSNE method to project down, to do a nonlinear projection down from a high dimensional space to low dimensional space, and to do it in such a way that what is clustered in high dimensional space still remains clustered in low dimensional space. And so here we did two things. So on the left, we clustered the result. We only clustered according to the geometries themselves, so not even yet applying the neural network. And on the right, we cluster the output of the neural network, that is the tight binding coefficients. And clearly this gives you a better clustering in terms of these band representations. So we use a certain color scheme here to indicate them. Okay, so I will skip this for lack of time, but I want to come to the last part of the talk, which is optimization. So here I have the full pipeline again, coming from geometry, going to band structure via the tight binding model. But now maybe you like some band structures better than others. Yeah? And so you can define a reward function based on the band structure. For example, in the simplest case, you just say, I like a high band gap for some reason. You can also parameterize your geometry. These are the Fourier coefficients, let's say, that generate the geometry. And then the beauty of having the neural network is that everything is differentiable. So you can really take the gradient of the reward with respect to the input geometry through all of this pipeline. And so that you can now use to do gradient ascent, to go to the highest possible reward, to change the geometry until you are satisfied and really have a nice high reward. And so I want to note very briefly at this point, optimization using neural networks, that's known as an interesting application. And here I just list two examples from nanophotonics. So for example, people have been looking into scattering from nanoparticles, train a neural network to get the scattered response and then try to optimize. Also in nanophotonic setups, for example, people have looked into photonic crystal defect cavities, the precise location of the holes, and then train a neural network and optimize through this. So that's a quick side note. And so now how we tested this is the following. Imagine you're a theoretician, you like to work with very simplified models, for example, a real physical implementation that gives you this band structure. So what is the geometry that can give you this band structure? And so we can define this in terms of a reward function. We say the first 6 bands should be as close as possible to the tight binding model. And here's a little movie that shows what happens. So to the right, you see how the geometry changes during gradient ascent when you improve the reward function. And to the left, you see how the band structure gets closer and closer to the desired band structure, which is shown in the background. And so now you can do this not only for one target band structure, but you can really do it for arbitrary parameters. Because even if you start with a very simple toy model, tight binding model, like the one shown here with 2 hopping parameters, it's not at all guaranteed that arbitrary choices of these parameters can then be implemented physically. Yeah. So maybe the refractive indices of the refractive index of your glass is simply not high enough to give you your strange band structure that is your target band structure. And so to explore this design space, what you can do is, what we have done here, what I show here, is you vary all the parameters, all the few parameters of your tight binding model in this case that defines the target band structure. And then
Florian,
for there's a
you
question.
will have about 5 minutes to wrap up.
Yes, okay, this is the last slide basically. So, okay. And then you can, for each parameter combination, try to optimize and see whether you can get a perfect match. And as you can see in this 3D plot, you cannot always get a perfect match. Okay, where do we go from here? I don't think I have time to discuss it. Maybe you can ask me in the question period. And so with that, I really thank you for your attention. Thank you.
Thank you, Florian. As we mentioned in the website, there is no clapping here, but there is this chat where people can put the clapping hands in the emojis. People are clapping. It seems to be questions now. We have about 4 minutes for a question or two. Let's see. So there is a question by University of Indiana Condensed Matter Physics. I'll mute them. Go ahead.
Okay, so I missed about the geometry. So what does it consist? Like, is it crystal structure plus the arrangement of particle and interaction as well? Like, or like it's just the crystal structure plus particle?
I didn't quite get the question. So the symmetries I'm talking about is just the symmetries of the geometry. So it would be, sorry. So for example, here it's just a C6 symmetry without reflection symmetry. And that is something that you want to put in to constrain the tight binding model for things to be more efficient, so that the tight binding model automatically will give you band structures that are compatible with these underlying symmetries and nothing else. But
I mean, we need to know the interaction, like whether it is like...
no, these are all non-interacting models. So I come from the field of designed engineered nanomaterials. So I'm thinking of electromagnetic waves or sound waves. So here I don't talk about interactions, but it's an interesting point you're bringing up. So if I do have interactions, then it depends a little bit. Do I really think of electronic materials with Hubbard interactions or so? Maybe that's a little bit in the future. But maybe you could also think about putting, say, a gas of cold atoms with some moderate strength interactions in some arbitrarily shaped optical lattice, as people can do these days. And then the neural network could be trained to first learn what would be the nonlinear, the density in the ground state of the system, which is already defined by these interactions. And then what is the band structure of excitations, like Bogoliubov excitations on top of this density. So this could be something that we could train the neural network to do. But right now it's non-interacting.
Thanks.
Very final question by Eliska, please go ahead.
So thank you very much for the super interesting talk, Florian. I have a question about this little bit of like vision connected to your final slide. Mm-hmm. Could I potentially use your method going via tight binding model also to say discover for example, new topological insulator, or I could only optimize around the new ones for some particular property?
No. So the idea is that you can basically discover arbitrary arbitrary structures. So to some extent, this is what we did here. I mean, the concept of fragile topological phases was known before, and probably our neural networks are not yet smart enough to, on their own, discover the concept. But here we could search the really large parameter space of geometries and find these 12% of these interesting structures. And then the idea is that once you have found one of these interesting structures, then you can optimize around it, sweep around, maybe get yourself constrained by fabrication constraints for these engineered materials, and find an optimal structure that not only gives you the features that you want, but is also easily fabricated.
Florian, I'm going to have to stop you here because it's already time. It was a brilliant talk. Thank you very much. And I think you went very, very nicely. Thank you.